So continuing right along, with discharge lamps, I'll finish those and get into the last of the lights story, LEDs and lasers. I'm mostly done, but for mopping up details. The basic issue here with the discharge lamps, so these are light sources that produce light not thermally. They're not making a hot surface radiating its thermal energy. They're working with atoms or atomic-like systems that fluoresce. And I just want to sort of make sure that's clear. They're working with quantum mechanical objects, little tiny objects that they're small enough that quantum mechanics really dominates their behaviors. And I'll focus on a particular group of such systems, the atoms. Individual atoms are just heavily quantum mechanical. You can't describe them classically at all. They're just, the electrons are wave-like, so they're so in-your-face wave-like that thinking of them as particles is not very helpful. And when the atoms go from one arrangement of the electrons in waves to another arrangement of electrons in waves, there's often a shift in the amount of energy the atom has. So in the case of trying to emit light, it's a shift down in energy. So they go from having a certain amount of total energy to less total energy. The missing energy comes out as light. And the remarkable thing about light, which I've talked about up until now as a wave, is that it also has a particulate character, a particle-like behavior. It is emitted and absorbed in discrete quanta, which are given the name photons. So I'm just rehashing this. So a photon is the smallest unit of light that you can have. You can't have a fraction of a photon any more than you can have a fraction of an electric charge, of a fundamental electric charge. There's a discrete character to a lot of the things in our world. It's a very tiny discrete character, but it's there. And so photons, you can have one photon, you can have two photons, three photons. You can't have 1.5 photons. And each photon carries with it energy, and that energy is exactly proportional to the frequency of the photon, of the photon's wave. And as we saw with world of radio waves, when you're transmitting a radio wave, a pure radio wave, not carrying any information, it's got a very specific frequency. If you start to play with it, turning it on and off, for example, now its frequency is a little wider. The same is true of photons. The waves that are associated with light are rarely absolutely pure frequencies. They typically have some spread of frequencies for reasons that ultimately go right into mathematics. You can't have a pure frequency that ever has a starting point or an ending point. It has to go on forever to have a truly pure frequency. So if it's got any time limit at all, it's not quite so pure. What that means also is that the energy is not perfectly sharply known in advance. The energy of a photon typically has a little bit of uncertainty to it. In fact, quantum mechanics introduces this whole idea of uncertainty, which I could go into, but I think I'll leave for the moment. All the little details, the things you can't quite know perfectly. The point here then is that these atoms, when they have extra energy, they can emit photons. The photons come out with a frequency that is directly related, it's in fact proportional to the amount of energy that was given up by the atom in shifting its electrons from one arrangement to another. What else about this? Oh, so that frequency, we see that as color. So if a photon comes out with a certain low amount of energy, it might be red light. If it comes out with higher amount of energy, having received more from the atom as it shifts from orbital to orbital, or from quantum arrangement to quantum arrangement, it might be in the blue. So you're seeing the energy spacing when you see the color. Is that okay? So neon, I didn't drag neon back out here, but neon has a very important rearrangement, one that shows up frequently after you have smacked a neon atom and put extra energy into it. You often have certain rearrangements that include these really intense ones in the red. That is, they give up just the right amount of energy to produce a red photon, as opposed to what? As opposed to an infrared photon, which would be of lower energy still, or somewhere in the other end of the spectrum of the rainbow, the violets, or off in the ultraviolet. All right? That's enough for neon. Any questions about when you see the color of a neon lamp or any other of the gas lamps directly, you're seeing atoms fluoresce? The name fluorescence is just this emission of light by way of a quantum rearrangement. I think that's a proper way of looking at it. All right? I then went on to fluorescent light bulbs. And fluorescent light bulbs, or tubes, I don't know what to call them exactly, fluorescent tubes are gas discharges too. They don't have neon in there. If they put neon in there, of course, it would be red, and illuminating this room with red light wouldn't be, it could be fun briefly, then it would be annoying. So instead, they use mercury in there. And why mercury? For a couple of fortuitous reasons. I mean, it's unfortunate that mercury itself is toxic, but they can put a tiny amount of mercury in that tube. It's milligrams, I believe, in the whole tube. Mercury it's a liquid at room temperature, which makes it fun to play with. Of course, it's hazardous, but it's interesting. But it also has a vapor pressure at room temperature. It's one of the rare metals that vapor pressure. It can be gaseous at room temperature and have a decent density of atoms rolling around in the gas, even at room temperature. That's part of what makes it hazardous, is that if you sit there with a pot of open mercury, you're actually breathing mercury atoms in the air. It's evaporating. All right? So it evaporates in the tube at room temperature just enough that there is a tenuous gas of mercury in the tube. And that's about the right density of mercury. Actually, ideally, it would be a little above room temperature. The tubes work best at about 40 degrees Celsius, which is a little above body temperature. That's their favorite temperature. The gas density is just right, based on evaporation alone, to make a really nice mercury discharge. To get the tube started is a little tricky, so they actually put another gas or two in there. So I think there's argon or nitrogen in there along with the mercury. But still, the tube is mostly empty. That is, it's got less than atmospheric pressure inside, and what is in there includes a very thin vapor of mercury. I think that's enough story about mercury. But mercury has the characteristic that when you run an electric discharge through it, that is, you get some initial charged particles in there, and then you expose those particles to an electric field by putting high voltage plus on one end and low voltage, maybe minus on the other, you get current to flow through it. When the current flows through it, the mercury atoms get smacked around a bit, and they start to emit, in particular, their favorite frequency of fluorescence. It's not red, it's ultraviolet. It's actually fairly deep in the ultraviolet. That is, it's way beyond the edge of violet that we can see. You truly cannot see 2480 nanometer, 248 nanometer light. It's way too UV for us. But it does a nice job of causing certain materials to fluoresce, where they take in a photon of the ultraviolet light, they throw out some of the energy they received in that photon as thermal energy, and then they re-emit a new photon of light at a different, and therefore lower frequency, less energy, lower frequency photon. And they can cover the visible with that. And so they put powders in those lamps that are carefully selected. They're mineral powders, in effect, not necessarily straight from the earth, dug up minerals, but they're inorganic powders. They're not built out of carbon, carbon-based molecules. Why? Because the carbon-based fluorescent molecules typically don't have a wonderful life. In that hostile environment of a discharge, they'll tend to essentially burn up or degrade. So they put in fluorescent powder that tolerates this environment, this discharge environment, sort of indefinitely without change. And it fluoresces white light. How white? Basically, it manages to have enough. intensity in the area that we see as red light and as green light and as blue light, so that together we see a white spectrum. It is not necessarily identical to the spectrum from the sun or from a tungsten filament, but it looks like that to our eyes. All right? So that's what you're seeing right now. You're seeing the fluorescence from the powder on the surface of the tubes. A few more notes about these fluorescent materials, the ones that take in a photon at one color and then re-emit at another color. Prior to, I don't know, 1950, give or take, there were fluorescent compounds were rare, things that fluoresce and emit a new wavelength when exposed to you send in one frequency, you get a different frequency. Those are pretty rare. You would see them like you go to a geology exhibit at the museum, and there would be a switch that you could press that would turn off the ordinary illumination and turn on a UV light, an ultraviolet light. And you would see that some of the minerals would glow green or something like that. I mean, those are still around. You may well have seen them, those kind of displays. But that was almost the only context in which you'd ever see something do that. Turn on ultraviolet light and you'd see things light up. Certain minerals do it. Clothing, for example, didn't do it. You guys are now used to having clothing that has chemical dyes in it that do this fluorescence trick, that take in photons at one energy and emit it at a new energy. All the neon colors, or your highlighters and stuff like that. And those chemicals, those are modern chemicals. They don't just show up. Otherwise, they're very rare. I think fireflies have them as part of the way in which they create light. They have fluorescent compounds in it. But basically, it's a handful of things in nature that have those in the organic chemistry of living organisms. We now have them everywhere. Even if you don't have one of those dazzling bright orange or yellow pieces of clothing on, you go to the beach, it's everywhere, right? I showed you last time that modern white contains fluorescent compounds in it. Modern white clothing, modern white paper. They put it in there to boost the blue end of the spectrum, because anytime you expose these fluorescent compounds to ultraviolet light, they take in ultraviolet photons, which have lots of energy, and they emit blue photons, which have less energy. Still a lot, but less. And off comes this enhanced blue glow that we associate with particularly white, fresh clothing or fresh paper. That's where we're just totally used to it, but it's new. On the grand scheme of life, it's new. All right? Any question about fluorescent stuff, fluorescent lamps, any of that stuff, before I just walk away from it? Yeah.
Is fluorescence a wavelength? Like, is it light or is it like not the same thing?
Is fluorescence a wavelength or light, or what exactly? Because I'm using it a little bit awkwardly, and I'm suffering with it myself as I'm saying it. I think technically fluorescence means that an atom or an atomic-like system takes energy in as light and re-emits energy as light, having played with the energy at least briefly. So this is as opposed to what? As opposed to like a mirror, which doesn't fluoresce. Yeah, the light comes back out of it, but it never really owned that energy. So technically, you can have fluorescence where you expose, for example, a sodium atom. We'll see sodium's favorite glow is yellow. And you can expose a sodium atom to that favorite yellow. It will take in the yellow, play with it, and send out the same yellow. And we'll see that actually happen. That's fluorescence still. It's just boring. The yellow went in and it comes out a new direction. So maybe that's a little bit exciting, but barely. What's much more interesting is the fluorescence in which some of the energy is consumed and lost as thermal energy, or principally as thermal energy. In which case, the energy goes in as one photon of light, and it comes out as a photon of light with less energy. So it's always shifted toward the redder end of the spectrum. If you send in ultraviolet light, it can return as blue light. If you send in blue light, it can return as green light. If you send in green light, it can return as orange light and works its way down. You can never send in red light and have it come back as blue light. That's a very exotic process. There are systems that can do that effectively, but they're really rare and special. So do I still have any fluorescent? One fluorescent item. Fluorescent earplug. Earplugs being kind of on my mind. This is an ultraviolet laser pointer, deep blue or ultraviolet. And so there's no orange light there. But if I send that at this earplug, you see it glowing orange, right? Pretty intensely. There's no orange light illuminating it. It's sending out orange light, having absorbed the ultraviolet photons and turned them with pretty substantial efficiency into orange photons. Is that okay? And as long as I use a light that has higher energy than the light that comes out, it may still work. So here's a green laser pointer. Get the same thing. We're taking green photons, which have higher energy than orange photons, and turning them into orange photons. If I had a red laser pointer, boy, I wish I had a red laser pointer, do I? Oh, very unlikely, right? They were so dime a dozen up until a certain point. I've got them downstairs. I didn't bring one. But anyway, if I illuminate this with a red laser pointer, nothing fun would happen because it can't build orange photons. Not enough energy. Yeah?
So you said energy was lost through thermal energy?
Yeah.
So if you kept shining the ultraviolet light, would it get hot at one point?
Yeah, if I keep shining the ultraviolet light, would it get hot? And the answer is yes. Because the energy is really going to thermal. So 20% or something, or you can calculate it actually, based on frequencies, of the energy is going into thermal energy, so it will get hot. And depending on how the molecules and stuff handle the heat, they may live forever and just simply get warm, or they may actually begin to degrade. And you've noticed that photographs, for example, or posters put in a store window for a year or two and exposed to sunlight, the colors start to shift. In particular, they lose the reds. A lot of old photographs and posters end up looking kind of blue. The red's all gone. Well, why is that? Well, because red dyes, red colors, absorb all the high energy photons in light. They absorb the blues. They absorb the greens. They absorb possibly by accident ultraviolets. And that's a lot of energy to absorb. What do they do with it? Well, they ideally turn it into thermal energy, but in fact, sometimes it just damages the molecules. And so red paints and dyes are particularly vulnerable to just wearing out. The photons go in and do chemical damage to them until they eventually stop having a color and no longer absorb anything. They just get kicked around until finally they're unable to work with light. And that's just bleaching in the sun. That was the classic way to bleach clothing or bed linen or something like that before the era of modern chemistry, basically. You would weave the cloth that you wanted to have white, and you would then lay it out in the fields for a week. And sunlight alone would just go in there, and any molecule that wants to be a red pigment would eventually just be destroyed by absorbing too many energetic photons and not being able to handle them. Okay? Yeah, all right. Other questions about anything about how fluorescent light bulbs work? 10 years ago, I would have said knowing how they work is super important because they'll be around forever. Well, that's not the case anymore. They're dying already. So these linear tubes, 50 years ago, that's all you had was these long, straight tubes. In the past couple decades, you've had these spiral ones, the compact fluorescents, and those were the big deal. And now even those are becoming, they'll become extinct eventually, I think, because you can do better with light-emitting diodes. All right. What else? Okay. Where I'll finish up and talk about discharge lamps is two other ones that are not fluorescent lamps in the sense they don't have that phosphor coating. And I've got them up here. This is a mercury lamp and a sodium lamp. So they use discharges in pure gases, pretty much pure gases. And these are both meant as illumination. And they're still currently in use, these kind of lamps, but they're also going to be, their days are numbered, I suppose, too. Let me start with this guy. And let me do this without any. I'm just going to turn it. Try that. So this is a mercury discharge lamp, but it's different from the one I showed you last time. and in fact from what's going on inside the fluorescent lamps, in that instead of being a low pressure mercury lamp, one where the discharge goes through a very tenuous gas of mercury, it goes through a fairly pressurized gas of mercury, lots of atoms in there. And the difference, to get that, I should say, to get that pressurized gas of mercury there, it has to get hot. Because mercury barely evaporates. It has a little bit of vapor above the liquid at room temperature. But to get a lot of atoms in the gas above a vapor, you got to go hot. Just like with water, you want to get a lot of water molecules in the gas, you go hot, make steam. So this sort of makes a steam of mercury. It takes a little while for that to happen. It's a couple minutes. Hopefully this is familiar to you in some places where they switch on the lights and the lights start dim and then they get brighter and brighter over the next couple of minutes. Your own children won't know about this anymore. It'll be gone. But this guy will take a little while to warm up. When it first starts, it will be a simple discharge in the low pressure vapor, partly mercury and partly something else, just to help the discharge get started. I may have argon or nitrogen in there just to help the discharge get started. And then as it warms up, something interesting will happen, and that is that as the vapor gets thicker and thicker, more density, that is more mass per volume, collisions will begin to become important. That is, collisions that occur between the gas atoms while they're in the process of trying to emit light. And instead of emitting the colors that they're used to emitting, that they emit at low pressure and density, they'll start to emit new colors. New spectral lines will start to appear, in part because instead of getting hit once, an atom getting hit once, given extra energy, and then very quickly working its way back down to the original quantum state, what's called the quantum ground state. It goes to an excited state. In a couple steps, it goes back to the ground state, emits specific photons, light comes out, that's done. In a high pressure environment, it can get hit once, it goes up to an excited state, it starts to work its way down, it gets hit again, and it works its way to higher states, and it gets hit again, and it has trouble working its way to the ground state, and it explores territory that it would not explore in its arrangement of its electrons. It would not explore in a low pressure environment. It explores a broader territory and emits a broader range of fluorescent spectral lines. You follow that, or ask me if not. So at higher pressure, you see things you don't see at low pressure. You see spectral lines you don't see, and we'll watch them show up. The other thing that happens is each spectral line becomes broader. So that instead of sending out a very specific frequency, and therefore a very specific spectral line and color, all that, which typically happens when an atom is allowed at its leisure to move from one quantum arrangement to another quantum arrangement. If collisions occur while it's in flux from one to the other, it may get hurried in the process. And in effect, the time over which with which it is building the photon and trying to narrow down its frequency gets abbreviated. And instead of making a very sharp frequency and a very specific spectral line, it gets broadened. The spectral line becomes fuzzy because there wasn't time to get the frequency under control. You shorten the emission time. The emission in time, you broaden it in energy. That is one of the Heisenberg uncertainty relations issues. So what I'm going to do, having talked now this plenty, we'll look through this camera, through that diffraction grating, the system that gives us an interference effect with which to see the spectral character of the light. And that is this guy. Yay. Okay. So I'm going to have it look at this high pressure mercury lamp. If we look straight on, we'll see it. And on the edges, you see the spectral lines? You see, can I zoom in on, let me zoom in on these guys. Actually, these are multiple orders of the interference, which is a whole other story. But Right now it's pretty weird color. It's got a lot of purple and stuff in there. And it's got very specific spectral lines, but new one, oh, stop changing focus. I just want you to stay focused. I'm going to try to zoom in and see whether I can. It's hard to separate them quite as much as I'd like. Can I get my? We'll see more and more lines show up as it gets hotter. And basically the light is getting whiter and whiter as the pressure gets higher. It's whiter because new spectral lines are showing up as we explore more territory, and the lines themselves get broader as collisions occur during the process of emitting light. So you okay with the ideas? Any questions about the ideas? This kind of tube has the characteristic that it takes a while to warm up, and if the power is interrupted for more than a very short time, the discharge collapses, it loses all the charged particles, and then it's hard to get them back. So you have to let it cool down before you can start the discharge again, before you can get those first charged particles there moving. They need room to move to accumulate energy in order to start knocking charges out of each other. So the discharge it's hard to start discharges at high pressure. You usually let the pressure go down low and then turn it up. So this is, for any of you who have had to deal with this problem, well, like at the gymnasium, there's a power flicker or something, some lightning strike or something, the power goes off for a second, all the lights turn out in the gym, and you have to wait 5 minutes before they come back on. They restart, and then they start warming up again. So I'll show you this. When we turn this guy off, we will not be able to restart it for a few minutes. All right, this is getting all washed out, so I'm not sure there's more instruction here except just getting dazzled. So let me turn out the power and try to restart it. It's on again. We lost it. So it won't restart until it gets cool. Any questions about a high-pressure mercury lamp? You've seen these guys in various places. They're pretty energy efficient, which is why they're used. They're also able to put on a lot of light, in contrast to most even fluorescents and stuff. They just aren't as bright. Okay, let me go over to the other guy. The other guy is a sodium vapor lamp. And here we are looking straight at it for the moment. So it's a glass envelope around a little tube, and the little tube is where the sodium vapor will be. Sodium is a very reactive metal. If you throw it in water, it bursts into flames in reaction with the water. And it melts at a fairly low temperature, but it really does not want to be a gas at room temperature. So this lamp will start, it's a discharge lamp, it will start using a completely different gas. Again, I don't know, it's probably argon. So the color will be completely wrong when we first start it. But after a few seconds, the sodium will begin to evaporate, and it will start to emit sodium's favorite color. Just as red is neon's favorite color, sodium's favorite color is yellow, a very specific yellow. It actually has two spectral lines, but they're so close together that you can't see them. We won't be able to see the difference between the two with this equipment. But you'll see a very specific yellow will show up. And historically, there was a time when things like roadways were illuminated with low-pressure sodium vapor lamps. That is, the sodium emitting its favorite color, which is this one yellow. And it was nasty to drive on a road illuminated with pure low-pressure sodium vapor lamps because you got exactly one color to work with. And it had the feeling, this eerie feeling of everything being two-dimensional. You couldn't perceive depth very well for some reason in that environment of pure one yellow illumination. So you don't find them anywhere anymore. They just were phased back out. They were very energy efficient illumination, which is why they were popular for a while. But they were horrible, just so specific, so monochromatic. So this is a high-pressure sodium vapor lamp. It's taking advantage of those same exact things I was describing in the high-pressure mercury lamp. Once the pressure builds up, which occurs as the temperature rises, Then you start having the sodium atoms begin to explore more territory, and they emit different new spectral lines that weren't there. And they also begin to have collisions during the process of emitting light, so that every spectral line becomes intrinsically broader. It's not as sharply defined in energy and therefore not as specific in frequency. That's the main thing to talk about. So it will start with a very specific yellow, and then it will get richer. Both new lines will start popping up, and the lines themselves will get broader. The other feature that I want to tell you about, and we got time to see it. When the pressure gets high enough, you get a strange behavior occurs in that original yellow spectral line. The original yellow spectral line, again, is at this one very special favorite frequency of emission from sodium. It involves, it's a radiation where one electron goes from an excited orbital to the ground state orbital. It's the last step in returning to the ground state. And so, as an atom that has just returned to the ground state and emitted this yellow light is perfectly capable of absorbing that same yellow light and going from the ground state back to the excited state. It's reversible. Right? It has extra energy, it emits light and goes to the ground state. That light can come along and add extra energy and return it to the excited state. It's just the same story backwards. And atoms work like that. If you expose them to the light that they were just able to emit, they're also able to absorb it and undo the emission process. It's the same concept run backwards, as though you reverse the movie. So, at high pressure, these atoms will continue to try to emit their favorite frequency and go to the ground state. But they will also be, all of them, very eager to snap up photons created in that process. And the photons, instead of being emitted and coming out where we see them, they're emitted and they go to an adjacent sodium atom which gobbles that photon right back up and then re-emits it. And another sodium atom gobbles it up. And so the radiation at that favorite frequency gets trapped in the gas. It can't get out because it just hops from atom to atom to atom. So what will happen is there will be a black line will show up in the middle of that yellow spectral feature where that light can't get out. Yes, it's being emitted, but it's being consumed as often as it's being emitted. And it's a feature of this phenomenon known as radiation trapping. All right? Hopefully that's followable. Hopefully we'll see it. All right, I'm going to plug in the lamp and turn it on. Okay, wrong color at first, and then the color we're looking for. So there's the yellow. Oh, stop this. That's as zoomed in as I get. Okay, so there's a special yellow. There's also some other stuff there from other gases probably. And now the yellow is getting, of course, brighter, but also it's getting broader, spectrally broader, which means that it's left-right, it's actually getting wider. And other colors are showing up more and more strongly. So these guys weren't there before. They're now showing up. And the color of the light, which started out very pure yellow, is now getting kind of more orangey and richer in color. And what I'm hoping we will see, can I get any more resolution on this? I'm not sure I can. Can I dim this down anymore? Got no control over anything here. I want to see the black. A black line should appear in the middle of this. I'm not sure these cameras are up to this. This is just, we don't have adequate equipment. I'm going to make a pinhole in front of that camera to try to cut down on the brightness, give us some more resolution. Yeah, it's hopeless. Nah, it's just not, you don't have it. Oh well. I should have planned ahead better. All right. Anyway, you can see it's gotten considerably more white. This kind of illumination you can tolerate. It's got a yellow tint to it, but it's not great. It's got a fair amount of real whiteness. Yeah?
How does the camera like pick up the red, green, blue light?
The spectral thing?
Yeah.
That's this grating that was in front of it. The grating, so here's the lamp totally washed out because I've got no control over its f-stop. It's unfortunate. I should just have my own camera. The grating has a series of lines. It's grill work. The spacing between the lines is like a millionth of a meter, like a micron or less. It's very, very fine. And so as a wave goes through it, the wave gets chopped into a whole bunch of separate, let me turn this off, I think I've proven the point. Separate little partial waves, which then go on, they spread out, each one is a ripple on the pond. And you've got all these ripples on a pond, and there are certain directions, right, like that one right there, where you get constructive interference for yellow light along that path. So yellow shows there. And for green, it's only right there. And what I'll show you is so with this laser pointer, the laser pointer, when it goes through this, will do the same thing. It gets sliced up into pieces, and only along one direction. Straight ahead, you'll get constructive interference, but often at a certain angle right there, you'll get constructive interference. And here it is. You see it over there? And then why laser pointer as opposed to a flashlight? It's because, first of all, laser pointer is one color, and second off, it's actually a single giant wave. This, in contrast to everything I've shown you up until now, instead of being buckshot, lots of separate photons that are unlike each other, this consists of the beam from this flashlight, laser pointer, consists of one photon copied an enormous number of times. So they're all identical. They're one way. They're all their electric field up at the same time, all their electric field out. And when you send them all through, they all interfere. The entire wave then is able to interfere constructively only at that one point on the right and only at that one point on the left. Actually, there are a couple of what are known as orders here. You can see this is the main one. That's the 0th order. On its left and right are the first order, and then there's the second order guys. There's a second order on my left. I don't see the second order guy on the right. Oh, there it is. Okay. So that's what the gadget was doing for us. And if I had this set up right with a camera that I could adjust make it so it could deal with the brightness, we'd see the spectral lines more well defined, and we would have seen that particularly that central yellow line. In years past, I've had it come out where you see that central line and a hole just picks up right in the middle, saying that there's no light coming out at the favorite frequency of sodium because it can't escape. It keeps getting snapped up by sodium atoms. The tube is essentially black at that opaque at that special wavelength. Other questions? So this is a story of discharge lamps. They're great. They're useful. They still get used in a lot of things. The projector lamps, so the lamp projecting up there, and I'll put this guy back. These projectors, the light sources are discharge lamps. So I think most of movie theaters use discharge lamps to create the light initially. Some car headlights are discharge lamps. What do they do for us that almost nothing does is they put an awful lot of light out from a small starting point, which is useful for optical things like where you're trying to make a projector. It's nice to have all the light originate from one point in space. Obviously, you want to have a lot of blues if you're trying to recreate interesting, for photographic purposes. You want a lot of blue, so incandescent lights light sources were never a very good choice for projectors. The one downside of discharge lamps, two downsides. One is that they tend to wear out. The act of trying to get current, the process of trying to get current to flow through a gas, it's got to start somewhere, it's got to end somewhere, and it typically starts on metal, it ends on metal, and you often end up gradually eroding those pieces of metal that are actually, they're inside the tube, or they're penetrating through some wall of the tube, and that metal evaporates. It's technically not known as evaporation because it's going right from the solid into a gas, and that's technically known as sublimation. But you can erode the metal, and the metal then migrates around in the gas and sticks to things, so it begins to dirty the wall of the tube. And eventually the discharge doesn't run properly anymore. You damage what are called the electrodes enough that the discharge fails. And the lamps for the projectors, I think they've got a life of something like 500 hours before eventually the damage that is accumulating by running this horrendous discharge through the gas finally kills them. So that's an expense. The other thing about discharge lamps is they're not, controlling the current that goes through them requires effort because they have an instability. The more current you send through them, the better conductors of current they become, because you're making more charged particles as you turn them up. You make more charged particles, which allows them to carry current better, which makes more charged particles, which allows them to carry current better. Hey, it runs away, and so you have to be careful to control the current flow through a discharge lamp. They do not follow Ohm's law. It's not like double the voltage drop, you double the current. Now it goes all crazy. So they have sophisticated systems to govern the current flow. All right? I think I've said enough about discharge lamps. Let me go on to a different topic, and that is LEDs and lasers. And as the years have gone by, LEDs went from being a novelty in this class to now we'll see how long I spend on them, but they're now front and center. You now deal with LEDs all the time, whether you identify them as such or not. And to understand them, I'm going to ask this question. How do the temperatures of a red LED and a blue LED compare when they're both emitting light? Yeah. Oops. Yeah, thank you. Better. And you could see, ta-da, okay. How do the temperatures of a red LED and a blue LED compare when they're both emitting light? Have you ever touched them? They're pretty cool. I mean, cool. They're not hot, okay? So how many think the red one's hotter? No. How many think the blue one's hotter? No. How about the temperature's about the same? Yay, good. Yeah, we're now way far afield from thermal emission of light. LEDs are really crafting the light particles. Temperature's got nothing to do with it, essentially nothing to do with it. So how do you work with these guys? LEDs and lasers, the reason I lump them together in part is because many of the lasers you now encounter are glorified LEDs, although the concept of laser is itself inherently interesting. They often have very pure colors. That's true of the LEDs as well as the lasers made from LEDs. An exception would be white LEDs. So this is a white LED, and really, this is a fluorescent system. This is still one color LED with some fluorescent material in there as well. So it's using the trick that the overhead lights are using of taking in photons in the blue and sending them out in the reds and yellows and greens. Okay? So anyway, these devices love to produce pure colors. They operate for a very long time before they fail. Usually the electronics fails before the LED itself does. LED lamps, they'll all claim to be 100,000 hour lifetime. It's never true. They always fail for some reason, but a lot of times it's basically their power supplies fail. Lasers can be dangerous to your eyes. We can talk a little bit about that. The light that's reflected from a laser hitting something has weird character to it. It's got a speckly character to it, if you ever looked at that. And that comes about because of interference effects and is related to the fact that the laser produces this single giant wave in most cases. And you get tremendous interference effects as a result, really enhanced interference effects. So the things I'll go through in talking about how LEDs work, and the first topic here that I'll talk is why can't electrons move through insulators? It might seem like completely off the wall. But the reason for going this direction is because in order to describe how LEDs work, light-emitting diodes work, I have to tell you how a diode works. And so in part this is an introduction to the world of modern electronics. So the LED has less in common with an old incandescent or Edison light bulb than it does with the computer processor in your cell phone or your laptop. So this is the beginning of the physics of how computers work. And here we go. So why can't electrons move through insulators? And the answer to that, which uses a word that I'm pulling out of nowhere, electrons can't easily change levels in insulators. What's a level? A level is another quantum standing wave. The idea is this, that we've seen how the electrons in an atom they're not orbiting little planets. They are electrons dancing in place in a quantum standing wave. And the different quantum standing waves, we call them orbitals because they're shaped, because they're around that central attractive positive core. So their standing wave character there, they can have different standing waves and associate with them as different energies. And I told you last time that energy is partly electrostatic, potential energy. How close are they to the attractive core? How far are they away from it? And it's partly kinetic energy, which has to do with how tightly the crests of the wave are packed together. Well, that's true for electrons orbiting a positive charge, but how about if you put electrons into a material that it's going to have, so you build a solid. And if you build a solid, and I'll make the solid, doesn't matter what I build it out, it's ultimately going to be comprised of atoms. So let's rip all the electrons off the atoms. Let's put all the atomic nuclei where they're going to end up. We'll place them there. We'll hold them there magically somehow. So they're there. We'll make it a rectangular box, and we'll put only the nuclei in so far, and we won't worry about their quantum behavior. They have quantum behavior, but it's negligible for our purposes. And now we start putting the electrons in. And it is true that the electrons would love to orbit one of the nuclei because it's very attractive, positively charged. But it looks around and it goes, oh, their other nuclei look good too. It can't make its decision. So instead what it does is it settles into a wave that explores all the whole box. It's a quantum standing wave of the whole box, somewhat structured by the presence of these little atomic nuclei placed fairly uniformly throughout the structure. And that quantum standing wave, it's not so much centered around a single nuclei. It's constrained by the environment of the box. And so we call it a level. And the level is really in reference to the fact that it's got a certain level of energy. In this case, the first electron that goes in there will go in the lowest level of energy it can. One electron in that level. And so it's a quantum standing wave that gets pretty snug up against all the nuclei whenever it's got an opportunity, because that reduces its electrostatic potential energy. And it also has the wave crests very far apart, so it's got very little kinetic energy. One electron in there. When you start putting more electrons in, you can put a second electron in that same level, according to Fermi's, the Pauli exclusion principle, but those two electrons have to have opposite spins, one spin up, one spin down, to distinguish them. But then, as you put more electrons in, you have to keep putting them into levels that are different standing waves. And they typically have more energy. So you work your way up in levels. I'll manage to give you insulators in a second here. Is that true? I won't do that. Let me just say that for an insulator, which is this question, when you put in enough electrons to bring the system to neutrality, when you're working with a material that wants to become an insulator, the last electron that you put in will go into we'll go into one of the levels. It's going to be the highest energy of all the ones that electrons went into, because of course it's the last. It wasn't given an opportunity to go into the lower energy levels of the others. But when you put it in that last level, you will have finished a grouping of levels, grouped in energy. And if you were to bring in one more electron, it would go into another quantum standing wave with much more energy than the last one you put in. The point is that you have sort of finished off a system of levels when you put the last one in that actually did go in. And they're all they're boxed in energetically. Those electrons, for them to shift into any other level would take a lot of added energy. And that constraint, where they're all packed in tightly, and I'm not going to be able to do this properly, prevents them from responding to electric fields. They can't carry current. And that's way too brief and truncated, but that's where we'll pick up next time, and I'll explain then why you can't get electrical conductivity in that kind of a system.